Okay, great. So we ended last week just briefly talking about this idea of regression. So it's something that you may have heard of before, maybe not. But essentially, it's just a very big umbrella term which answers the scientific question, how much? So if I say, I have so much of this and that, a regression model will be able to predict something based on those values. So last week we ended with sort of a simple example, but if you're not familiar with looking at math equations since being in school, that might not feel as familiar. So what we're looking at here is essentially just like a formulation of a line that's trying to formalize a scientific theory. So we're going to spend a little more time with this today in the actual lecture. But what's important to note here is that we have something that we're trying to predict. In this case, this is y. So maybe we have something we're trying to investigate called number of measures a piano player is able to memorize. And we're trying to predict that number based on two other things that we think are going to contribute to that. So maybe that's something like the number of hours that they've practiced a piece of music, and the other one is the number of years they've played piano. So logic is basically, if I know these two things, I can have some sort of rough approximation of what I'm trying to estimate in this case. And we'll see a very clear example of that after we sort of review here. We briefly looked over what this sort of means if you had this for a single individual. So if you have a little mathematical model like the one in the middle of the screen that says y equals 2.3x1 plus 1.05x2 plus 7, and I tell you what those x1 and x2 represent, and then I also say I know someone who's practiced 10 hours and has 3 years of experience, what you can do is just plug and chug those numbers into the equation in order to get an approximation of how much of whatever your dependent variable is. So I wanted to end last week with a bit of a discussion talking about some of the advantages and disadvantages with this, but I just want to briefly go over this together as a group and not belabor it too much. So some of the advantages of using a model like this is that it gives us a common language to discuss the assumptions that we have as people trying to do scientific research, especially within music. There are clear ways in which the model can be wrong to different extents. So we can say, hey, if I put this one number in, it's quite helpful and it's good at approximating the data that I have, which we'll see in this lecture. But this other one isn't helpful at all. Or whenever I put numbers in, it completely gets it wrong. So it's a way to formalize the ways that we can be wrong. So it allows us to be falsifiable. It will eventually allow us to give us the ability to incorporate uncertainty into different measurements, again, which is the subject of today's talk. And it removes what is special about each individual case. So one thing that's quite different about research in music psychology and music science and music neuroscience is that you're not really interested per se from a research standpoint about what you or me or your aunt who plays the piano does. You're interested in much larger general trends. So a lot of the times we'll read articles in the next coming weeks, and people will be able to say, well, yeah, that makes sense in this case, but I have this one friend and he's never practiced and he's actually quite good at the piano. And that might be true, and that's not to discredit and say it's not true, but remember what these models are trying to do is summarize basically the pattern of a lot of different people as opposed to really describe one thing very well. Moving to the disadvantages side of this, it's quite reductionist in the sense that it doesn't care about what's special about each individual case. So if you're doing an analysis of a piece of music, it doesn't really serve the music well to basically say, well, this person's doing this, but all these other people do it kind of this way. So it's kind of like a middle line approach. Like what you're really trying to do is say, this is why this one person at this one specific juncture in history made this very specific artistic choice. And that's not what we're doing here. And it's important to differentiate that. So we'll never capture all of the different nuances involved with the task at hand. There's always going to be a but what if, or what about this? And models can be quite deceiving in how they represent what is important to the world. And we'll see examples of that today because it sort of removes what is special about each individual case. So with that in mind, let's jump to our lecture for today. So before starting this other one, does anybody have any questions about sort of high level regression stuff or things that we talked about last week? You could either say, no, I don't have any questions in the chat, or raise your hand, or maybe type something out in the chat. Say that you're intrigued by the idea of regression. So no questions from Paula, thank you. Anyone else? Just try to take the temperature of the class. If you're finding it a little out there, more mathy than you signed up for a music course. Okay, great. Some no questions thus far from Eric, Maria, Josephine, Daniel. Perfect, perfect. Okay, so with that as our kind of basis, we're going to be jumping into the last of our lectures, specifically talking about sort of philosophy of science and how that intersects with music, with musical examples. So I've titled this lecture, Eureka, I've discovered C major, because I thought it was a bit provocative in the sense that, you know, do you actually discover something like C major, or is it something that's possibly invented? Those are all types of questions that we'll be thinking about today when we make assertions about what we believe actually exists in the world and how we try to kind of formalize that. So when we talk to someone else, we're all on the same page about talking about specific examples. So again, the quick summary of the lecture to kind of prepare you what we're going to talk about, or if you're going to tune out for the rest of this because you have some other assignment you have to work on, or you're like, whatever, or you just want the quick summary for it. The world and the data that we collect is quite messy. And we'll see that, and we'll see very specific examples of what that means. So we need tools because the world is messy in order to be able to discern if we're just looking at noise, meaning just completely something random, or something that's actually real that we've found that's like a pattern in the world. In order to do this, we have the tools of statistics, which are used to quantify, I say used and abused, because we can see how we can sort of mess with this, to help quantify how much uncertainty we're looking at when we're actually looking at data. So when I use the word data here, I'm using it very specifically in this sort of like empirical sense of the word like that a scientist would use. So empirical just means that you can observe something. So you could say that something like musicology and historical analysis and music theory is also empirical. But it kind of takes on a different angle when we're talking about generalizing data in a scientific context. So, here's our regression review. The points we just want to make, I know we briefly talked about this, but we work with models to make problems about the world easier to understand. When we do this, the world is not deterministic, meaning that every time you do and start in one state, that something else happens in the exact same way. And that the importance about regression and working with models is that we need the ability to quantify how much uncertainty we have in what we observe in the real world. And I know I've been talking really theoretically up until this point, and I promise I'll give you tangible examples for this. So we talked a little bit about what a model might look like. And in the slides before, reviewing last week's, I showed you this as a mathematical thing, but now I'm showing it to you as what it might look like if you just had a model that was in the form of a graph. So we're going to take a similar example in terms of what we talked about this week. But it's the same in that we're going to be using a mathematical model like this to make explicit our assumptions about, in this case, we're going to be looking at practicing, which is, I think, something that a lot of people have familiarity with. And the good thing about using models like this is that they state sort of what direction we think things are going to occur. So if someone practices more, do you think they're going to make less or more mistakes? Could I see an answer in the chat? Just to make sure we're all on the same page. Hopefully less mistakes from Paula. Thank you. Yep. And then importantly, too, we don't necessarily just want to know what direction the relationship is in, right? We don't want to say, oh, if you practice more, you make less mistakes. One thing that you really want to know as a scientist is you want to quantify the magnitude of this relationship. So does it matter that the more that you practice, the less mistakes you make? Or maybe is it in a situation where there's a certain amount of diminishing returns? So you maybe practice, there's no real difference in performance between practicing 3 hours and 4 hours every single day, whereas there is a difference between practicing, 1 hour and 0 hours. And that's really important to be able to understand because it can translate into basically time spent in someone's life and say, hey, actually, there's a lot of evidence to suggest that extra hour of practicing after 3 actually might, either not help or maybe even hurt you. And it's important to be able to formalize this as we do as scientists. Okay. So the real question here, what changed, is that if we collect some data, the real question we're going to be answering is how do we know if we've actually found something? And we can get this from a couple of different ways. Oops, I'm pressing the wrong button. And which is going to be this focus of today's class. So we're going to be wondering, so where do all these numbers come from? I'm talking very theoretically here. I'm totally making up numbers in terms of what these models mean. And the sort of answer that we're going to be getting to is that either comes from previous research or we can actually learn these relationships from the data themselves. And again, we're about to dive into this. So our learning goals for this class is going to basically have a tour in knowing how do we decide if we actually discover a real relationship when we collect data. And then as we go through this story that I'm going to tell, we sort of know what could go wrong in this process. And that's really important to think about. And what I really want you to do throughout this lecture, it's going to be a lot more narrative from my part, but I'm going to be asking for a lot of serious critique from your part as we go. And the whole idea is that after we go through this scenario together, in terms of try to discover if we did find something when we're listening to this story that I've created, can we transfer that when we actually start critiquing literature in music psychology, music neuroscience, music and psychoacoustics? So my plan for this lecture, instead of giving you a boring description of this thing called null hypothesis significance testing and then trying to explain to you what a p-value is, we're going to instead do a walkthrough of sort of like an experiment narrative that I've created here. We'll note new terms as we encounter them, highlight what might go wrong along the way, and then notice points where that we should be skeptical when assessing data. So I'll take a minute and I'll read this scenario out to you, but it's really important that we understand this because this is going to sort of be the foundation of what we'll be talking about over the next 90 minutes together. So imagine you are a music psychologist who is interested in music learning. You have read some papers about the effects of practice in learning a new language and want to see if you can find a similar relationship in music. To do this, you plan an experiment where people are told to practice a piece of music on the piano. They record how long they practice throughout the course of the week, and then assess how many errors they make at the end of the week in a performance in your lab. So before we start diving into this in terms of stats and thinking about like that, I want to review this in terms of framing our research question in terms of a larger scientific question. So if you've already looked at the slides to this, feel free to also contribute. But if not, this is going to be a bit of review from lecture 2, just to make it remind you that this doesn't happen in a vacuum. The reason we're doing this is because we want to understand this within a larger theoretical framework. So in lecture 2, we talked a little bit about the difference between a framework, a theory, a hypothesis, and data. We're going to look at each of those with this specific example. So we can either raise your hand or answer in the chat. What do you think would, in this scenario, best describe the framework that we're talking about? So what phenomena do we want to describe in investigating this experiment? Why are we doing what we're doing here? Maybe you're answering the chat. If you'd like to unmute or raise your hand, I'd be more than willing to call on you. And of course, I'm not expecting people to have perfectly formed answers for this. Okay, so we have some answers in the chat here. So does improving your instrument make you make less mistakes? Okay, that is on the right track, Matteo. We want to find about the correlation between time spent practicing and errors in play from Merrick, and learning and how practice could accelerate it from Maria. Yeah, so I think Merrick, Matteo, you're definitely on to the right direction here. But specifically what you're saying is a narrow testable statement, and it's kind of closer to what we're talking about when we talk about a hypothesis or theory. Maria, you're definitely on it in the sense that we're talking about learning, and we're having a specific example of music learning. Alexander says the phenomenon of the correlation between practice time and skills of improvement to be measured in some way. Yeah, okay, so we're all in the right ballpark here, but I'm just trying to get a bit more specific about the scientific terms we're using to describe this. So I would say, if you haven't clicked through the slides yet, is that we're talking specifically about learning here. And music learning. There are aspects of performance also involved that we want to consider, because we have to think about how do we assess what is actually learned. And also it's worth thinking about what do we actually mean by learning. And of course, if you're into this, there's a litany of articles that you could read to think about this, but we're not going to belabor that right now. All right, moving down on our little framework, what would our theory be? So if we think, as a couple of people here have said, that there's this relationship between practicing and the number of mistakes that you make, why does this occur? What is our theoretical framework for talking about this? Remember, a theory, as described in that Guest and Martin article that we're going to return to several times, is a set of causal relations that attempt to describe, explain, or make predictions about the world. So why does practicing work is really the question that we're answering here. So let's see a couple of possible answers about why you think, why does practicing work? How come if you just do something over and over again, like why does it work? I trust some people are typing something in the chat. This question is particularly of interest if you're have aspirations to be a music performer or a music educator. Matteo says kinesthesia.
I don't know if it's correct in English, actually.
Oh, I see. Like a kinesthetic.
Like the memory of the muscles.
Yeah, like the memory of the muscles, right? So that's getting close to it, right? Yeah. So there's an idea there's a link between memory and your ability for your muscles and fingers to move in a certain way. Yeah, you're scratching at the right surface, but hopefully you can get more specific. Like, why does it actually work, in the sense that, you know, if you're trying to play something faster, you start slow, you go again. You know, what's actually going on in your brain that would explain why this happens? And it's difficult. Like, if you've never thought about this before, it's hard to think. You just sort of take it for granted, right? That, like, if you practice, you get better and you make less errors. But remember, from a scientific point of view, we really want to think about the theory behind this, because if we really understand the set of causal relations that's happening inside your body when you practice, we can make adjustments and help people even sort of practice better or understand things about the mind. So I won't go into it, more of it here, because I think a lot of people are probably like, I really have never maybe even thought about this before, which is also okay to write in the chat. And so what I would kind of set this up as, and this is just one way to think about this, this might be an example of something called Hebbian learning, which is this idea that if sort of neurons in your brain, and I'm going for a neural explanation here as opposed to a behavioral one, if they sort of fire at the same time, they wire together. And this is this idea of like neuroplasticity and learning, in the sense is that if you activate the same sort of like constellation of neurons in your brain over and over and over again, your brain sort of begins to expect a certain pattern to occur. It's like, oh, I've done this before. And because you're, you know, asking your brain to do this over and over and over again, it becomes more efficient in this process. So you're making a more efficient neural pathway through repetition. So if you haven't really thought about this before, it's maybe kind of like a sled going down a fresh, new hill of snow. So if you've ever done this before, the first time you go down a hill, it's kind of like slow, it's nice and powdery. But of course, if you go down that same path over and over and over again, the snow is going to get more compact, and you're going to be able to navigate that specific path that you've carved out very, very well, to the point that you're going extremely fast by maybe the 10th or 20th time that you've done this. This assumes that the learning isn't dependent on the subject matter. Notice that there's nothing specific about music here. And this relates back to our larger theory, in that we know from previous research in this example that something works with language. So our assumption is it might similarly work with music. All right, moving down, we're going to skip specification and implementation for now. And let's go now to the hypothesis. So what hypothesis do we have working within music learning, specifically this idea of processing facilitation with practice? What is a narrow testable statement that we can actually say, I think this is going to happen, and importantly, I could be proven wrong in a specific way if this doesn't happen? And I think this is very close to what Matteo was saying before. But could you reword it, Matteo, or someone else chime in? How would you turn this idea we have into a very specific, narrow, testable statement? You're in an argument with one of your friends at the pub, and they say, actually, there's no relationship between practicing and the number of mistakes that you had. So you say to them, well, if that's the case, then I would expect that this, hoping to be saying that you could be proven wrong, but knowing that you wouldn't. Yeah, people can improve their skills by practicing. Great. From Paula. So that's a very simple way of describing it. And we can have different versions of these hypotheses, right? So just like we talked about our example trying to predict the weather in Berlin, and also talking about the example of memorizing music from last week, we could have weak and strong versions of this, right? So as time amount of practicing goes up, errors go down. And in that specific situation, we're not saying how big that relationship is. Like, what if it's very, very, very small? Like, a lot of time goes by of practicing and your errors go down a little bit. Is that evidence that this type of learning occurs? Maybe, maybe not. Whereas you could also have a strong version of this where we specifically say, I think this is exactly how learning occurs. So for every minute practiced, the amount of errors in the specific context will go down by a set constant number. So we can get these strong hypotheses from previous research. So maybe there's something to suggest what the rate of learning is inside language learning. And we're interested in, is it the same in music? And it's important to note that usually we're not the first ones to ask this question. We're not coming along and saying, no one's ever looked at learning before, right? Like that would be ridiculous in 2020 to assume that. And then lastly, what we'll look at is what data would we want to collect in order to investigate this? So I have a specific example prepared, but if you just had to sort of whip together a small experiment for this, maybe someone can raise their hand and answer this. Like, how would you design an experiment to investigate whether or not, oh, sorry, I'm thinking of a different lecture I've given. In this example from our scenario, I'm sorry, what is the data that we are collecting? What are we going to use in order to investigate whether our hypothesis is true or not? So if you have the slides up from the PDF from earlier, you can look back on them or sort of think about our scenario here. And again, yes, Josephine, time spent practicing and mistakes made during performance. So of course we have to think about this. Time spent practicing, what unit do we want to measure it in? Do we want to measure it in seconds, minutes, hours? Is there or are there advantages to picking one over the other? And simultaneously, what counts as a mistake? And this is all addressed in our next slide here. So of course we have to create a design of the experiment. We're going to assume time will affect number of errors. We come up with something from our scenario where we give a piece of piano music to a bunch of different people. We don't necessarily mind who. And we ask them to document the number of minutes practiced. So it is worth thinking to yourself, what unit are we measuring all of these things on? What could be advantages and disadvantages of picking smaller and bigger ones? And then how do we count the number of mistakes that we make? Do we create a list ahead of time about what counts as a mistake? That could be one way to do it. Or maybe we could ask two people to judge the performances, give them a set of criteria, and look for some degree of inter-rater reliability between them. So if we say, okay, these two people tend to basically just agree about how many mistakes were made, and that this inter-rater reliability is high enough, which a way that we could calculate it, then we say, yeah, it's good enough. We're going to go forward with our model. Great. So getting more specific about this, the number of minutes practiced in this sense is going to be referred to as our independent variable, whereas the number of errors that we're going to be detecting is our dependent variable. So the independent variable is the thing that we think that we can manipulate in order to get a change in the dependent variable. So the dependent variable would be what we think can be changed based on the manipulation. So if our dependent variable is number of mistakes, and we are trying to predict it in terms of number of minutes practiced, can you think of any other independent variables that we might be able to manipulate instead of minutes practiced that would change what the dependent variable is, or change the amount of the dependent variable? So what else would affect the number of errors in a piano performance? Age, maybe. Good. It's the skill of the performer. Great answer. Time spent practice before the experiment. Wonderful. How they practiced. How many people are listening? Yep. Stress. Perfect. Okay, great. These are all good examples of different independent variables. Difficulty of the piece, perfect. So there are ways to incorporate these simultaneously if we start talking eventually about the idea of what does it mean to statistically control for something. So we can think about this in terms of a mathematical regression model. But more important to this lecture is just knowing that those would count as independent variables, whereas the dependent is the thing we're trying to predict. And sometimes that gets confusing for people because they sound quite similar. So if we were also interested in learning and music learning, what would be also another dependent variable that we might look into? So here I've arbitrarily decided number of mistakes that are made. But if we're looking at learning, what else could we look at to say that we have found evidence that learning has occurred? So the same idea exercise, but for the dependent variable. Less mistakes occur while playing than in the beginning of the experiment. Yeah, that's something we could do, Marek, but try to get away from the idea of mistakes. So imagine that we're not looking at mistakes as a quality of, as something to investigate for learning. So think about learning more generally. We're interested that more time will result in more efficient practice. Yeah, memory is something, Paula. Yep, what else could we have? Let's take one more and then let's move on. Ability. Yeah, okay. And ability is an interesting one, Matteo, because you'd have to kind of figure out what do you mean by ability? How are you going to quantify that? And is it close to what we're interested in investigating? Okay, great. So let's move on with the actual experiment here. Josephine says broader understanding of the instrument or music in general. Yes, definitely correct. Okay, so moving on to our plan here. So we've got this idea. We've designed an experiment together. Our next goal is to find 20 people that are going to do this for us. We're going to ask them to practice the first 20 measures of a piece of music. So everybody's working about on the same amount of music. And we ask participants to record themselves whenever they're practicing. So maybe they do this on their phone or we give them a voice recorder. And the way that we get our independent variable, which is the number of minutes practice, we're just going to use the number of minutes of video that they used. So why might we want to do this as opposed to just asking them how many minutes did you practice this week? Especially if you're asking people who are playing music, why would it be important to find a way to get a more exact measure? And I know that's kind of the answer, but especially when contrasting this to something like self-report. Daniel's raised his hand. Would you like to take it?
It just allows you to have an exact number of minutes that they actually practice rather than them just kind of guessing it. And there's always the chance of them over stating or understating how many minutes they actually practiced each day.
Yep, exactly. Say Maria chimed in and said that also as well, right? So we know that people are not good at probably reporting exactly what they're doing, especially if this has like a value judgment attached to it, right? You know, people might be encouraged to underreport the amount of minutes that they practiced if they feel they didn't practice that well. You know, throughout, or they know their performance is going to be bad because they might feel it reflects on their ability as a musician. And that's something that we want to consider if we want to have an ecologically valid experiment. Okay, so the participants come in then to the lab at the end of the week. They perform their piece. We count the number of errors that they make, and we put all the data into a spreadsheet once we figured this out. So the question then becomes, let's look at the data. So I've generated some data here. I'm looking at it in terms of a spreadsheet. And the question that we then want to ask, do I have a slide for this? Is, do we have evidence of learning here? So I present this to you and I say, look, we've done it. I figured it out. I have evidence of learning. Are you convinced? Yes, no. Okay, why, Merrick? Do you mind unmuting and telling us why aren't you convinced that we have evidence of learning here?
Because we just have raw data.
Yeah.
We don't have any kind of analysis in it. Therefore, because we just have, when we want to analyze it, we have to put all the data in relation to each other, and then we could guess if the statements, if the statement of learning correlates to the errors in practice is right or wrong.
Exactly. So hopefully, yeah, you're not like, you don't look at it and say, yeah, that's good enough for me. It's in a spreadsheet. It looks like science. Let's call it learning, right? I also have a small advertisement here. If you ever do empirical data, there's only one way, in my opinion, this is an aside, in which you should set up spreadsheets, and it's called tidy data. So notice here that the way I have set it up is each observation or each participant is set up as a row, with each variable being a column. And note that we only have one type of data per cell. So notice that in the minute practiced column, it doesn't say 5 minutes, 8 minutes, because that would be two types of data. One, the magnitude of the minute, and the other noting the actual unit, which is minutes. One of you will probably listen to what I'm saying in like 2 years down the road, be like, oh, there's a specific way in which I should set up my data, or maybe more, definitely more than one of you. But I want to make that advertisement now, because if you set up spreadsheets like this, your life will be 100 times easier if you ever do work with data. Okay, so back to the actual lecture. So what do? Okay, let's find a different way to look at it. So what I've done here now is I've taken the data that we have from our experiments. So this is some data that I've artificially generated, and I've plotted it on something called a scatter plot. So note here, if you've never looked at a scatter plot before or don't know how to interpret it, each participant in our experiment is going to be represented by a point. So you can sort of see that one of the experiments, the top left, is someone who's practiced approximately 5.1 minutes and made about 16 mistakes in their performance. Whereas if we look all the way to the point on the bottom right, that represents someone who's practiced for about 13 minutes throughout the course of the week. People here aren't practicing that much and have made about, looks like 7-ish errors, or 6.89-ish errors. So at this point, I would ask you, we're again looking at data differently. Do you believe now that we have evidence of learning? Is question number one. Are you convinced we found music learning? I'll take a hand raise. I'll take a message in the chat. We get Daniel again. What do you say?
I feel we have evidence that there could be learning, but we probably need more, or I'm not sure, like there's evidence that there could be, but we haven't excluded any other, like all the other reasons for the different number of errors, maybe.
Okay, that's something. Can we hear from someone else? Merrick says not yet. Would you like to say why you don't believe there's evidence of learning?
Yes, because actually to have a regression, we need to draw a line between all the points. We have to figure out, I guess, I'm not quite sure, but the arithmetic mean between all the points of data. So that we would have an actual regression, and then the direction of the line that is drawn would indicate that we have an evidence.
Great. So you're suggesting that we take the data that we have here and summarize it with a statistical model. That's exactly where we're heading, which is really good. And yeah, Matteo's saying maybe more with the tendency curve. And also, it's important to note what Daniel said, attending to the last point on this slide, which is how do we know that this pattern of data didn't happen by chance? So he mentioned that there might be other factors that created this pattern of data, right? So we could be looking at total noise right now, and that's something that we need to be able to figure out how to do. So looking at our next slide here. So it's important now that basically we look at this data, and we're just looking at raw data, even though it's a lot easier now in the sense that it's not in a spreadsheet. And we need to be able to quantify that something is happening here, right? We look at the data and it looks like as number of minutes practices increases, it appears that number of mistakes in performance decreases, which is what we wanted, right? That's what someone said was going to be our hypothesis. So our way in able to begin to quantify this is where statistics comes in. This is why we need statistics, is because we want to be able to quantify how, like, where are the errors in the world, or how much errors are, oh my gosh, basically the extent that we have errors in our data. You know, are we certain? How much error is there? Now, there's not just one school of statistics. There's a few different ways to think about this. And I tell you this not to overwhelm you, but just to sort of let you know that there's not ever just one way to go about doing things. One school of thought is the world of null hypothesis significance testing. So if you've ever seen people complain about p-values or try to interpret p-values, that's one specific school that sort of like thinks about a certain, you know, data analysis should be done as a very specific way. In addition to that, there's also Bayesian statistics, something that's become much more popular recently because of computers becoming a lot better. But there's also a third one called likelihood, proposed by this guy named Royal in, I want to say, the 70s or the 80s, that also is a way to think about how statistics work. So don't worry too much about each of these for now, but what we're going to do is focus on the first school, which I'm abbreviating as NHST, for null hypothesis significance testing. And this is the world of p-values. So whereas personally, I kind of like the Bayesian way of thinking about things, most of the scientific world at this point still operates within NHST, or null hypothesis significance testing. And it's important that to be able to understand the literature that people are producing right now, that we get how this works. So what is our problem? We want to be able to say that something exists, right? But this is running into our problem of induction, which we talked about before. In the sense that, you know, we could have scenarios where what we might get a piece of data, or we ran an experiment where people made no errors with little practice, or people who practiced a lot never actually got better, which is something that, you know, I think a lot of people who practice sometimes feels is the case. You work and work and work, and it doesn't feel like you're actually getting better. And if we just kept collecting data beyond the 20 people here, like, our data and the experiment that we have could change accordingly, right? So we get a bunch of people who are very good and they didn't practice at all, but they make no mistakes. You know, that would skew what we have. So we need to kind of find a way to say, okay, how do we know that this is actually a thing? And if we just keep adding data, things aren't going to change. And in order to do that, the world of null hypothesis significance testing sort of pretends, or actually assumes, that when we collect a certain amount of data, we're kind of taking a snapshot about what the world is actually like. So we're sort of taking a little camera and saying, okay, I'm just going to take everything, I take a little picture of it, and say, this is sort of representative of the true state of the world. This is important because it's going to help us get around some of these induction problems. But more specifically, what it does is it sort of takes the problem of induction that we talked about earlier. And what we're going to try to do is exploit this asymmetry, which we'll explain, that exists in that it's easier to take down a theory rather than accumulate an evidence for one. So let's jump to the next slide. So the idea here is that instead of providing evidence for a theory happening, so we're not going to say I'm finding evidence that learning did occur. Now prepare yourself, this is a bit confusing. What we're going to try to do is find evidence that nothing is not happening. So I'll say that again. So instead of trying to find evidence to suggest that we do have learning, we're going to try to find evidence to say, hey, well, we know that nothing isn't happening. And if nothing isn't happening, what are we left with? Well, hopefully we're left with something happening, right? So the whole idea with this is we're going to, if we take down a theory that nothing is happening, we're left with something must be happening. And if something is happening, we refer to that essentially as statistical significance. Of course, it's more complicated than that, but for a first lecture in which you're not signing up for a stats class, this is essentially, I think, enough that you have to know. So this logic is difficult to grasp. We're going to take a couple of attempts at it if it feels unclear for right now. But also know that there are people who literally have careers in science who I believe also do not understand this to the extent that maybe they should. So don't worry about that. I see a comment from Merrick that I missed from a few minutes ago saying maybe we could create a test group. Yes, we will be getting to something like that very soon, but that comes with time. So to get a little more specific about what I mean between something happening and nothing happening, the idea with this statistical significance testing and null hypothesis significance testing is that we would want to compare to know if we found something with what would be the case. You have to imagine a world about what would the data look like if nothing was happening. So if you direct your attention to the left part of the slides here, hopefully when you look at this data, you can kind of see that there's no relationship, or you wouldn't guess that there was one, between the number of minutes practiced and the number of mistakes made in a performance. We see near the left side of the left graph that there are people who practiced a small amount and made low mistakes, as well as a lot of mistakes. And that pattern continues as you progress rightwards on the graph. This contrasts with what we saw from our plot from before, which is a situation where something is happening. As the number of minutes of practice increases, the mistakes here decrease. So how would you then sort of formalize this notion? So how do you then sort of take what we see here and sort of summarize these things? And that's kind of the question that we're asking. In order to also introduce some terms here, the world of null hypothesis significance testing also has two terms to describe both of these worlds that we're comparing. On the left, we have H0 if you're an American, or H0 if you are British. And that describes sort of this state of the world in which there is no relationship happening. On the other side, H1, sometimes also referred to as the alternative hypothesis, is the possible world in which something is happening. So we'll go back over these a few different times, but it kind of describes basically a little thought experiment we need to consider in order to decide if something is happening or if something isn't happening. So taking a point from, I think it was either Matteo or Merrick said, what we would want to then do is try to take our data and summarize it with, in this case, a line. So on the graph on the right, the data that we actually collected, we do see a bit of a trend, right? So we see that if we summarize things with essentially what is the arithmetic mean in 2 dimensions, that as the number of minutes practice increases, the mistakes decrease. This contrasts with a situation on the left, H naught, where as number of minutes practices increases, the number of mistakes doesn't increase or decrease. Now, if you look very carefully at this line, is that line perfectly 0? You can answer in the chat. So is the line on the left perfectly 0? So we're seeing a no from Daniel and Merrick. Has someone I haven't heard from today, can you explain why it's not perfectly 0? So either Josephine, Maria, Paula, a couple of other people I haven't heard from today, Yelena, Hannes, Florian, sorry, Alexander. Why isn't that line completely 0? Or said another way, why isn't the graph on the left evidence that as practicing increases, number of mistakes also increases? Any guesses? I'll give you the answer because I know it's probably a lot to think about. But hopefully you've thought about it yourself a little bit. In that we're looking at data from the real world, right? So there's a certain amount of chance and variability associated with everything. So on the left, we could have collected data from an experiment in which there is no relationship, but we did find something, right? So we need some sort of tools, and that's the whole point of statistics, is to give us some sort of machinery and systematic way to say, yeah, it's basically 0, but not exactly 0. So it doesn't have to be exactly 0. It has to be just kind of 0. And on the right, we have a relationship that's definitely not 0. All right, great. So we're getting almost to our break here. I know it's a lot. And then we'll get to this. So essentially what we're going to want to then do is run a statistical test to show that the slope of the line of the data that we collected in our experiment, shown on the bottom, is not 0. This is compared with this imaginary situation where nothing is happening, shown on the top. And it's important to note that the size of the slope, or how big the slope is, or its magnitude, will tell us how strong the relationship is. And this is something that's referred to as the effect size. So if you have a very steep line, what would that mean in this context? Maybe in the chat. What would it mean if there was a very, very steep line, steeper than the one that we see in the bottom graph? I'll take a raised hand, or maybe an answer in the chat. Even stronger correlation. Yep, stronger coherence. Alex, great. As time practiced had a strong impact on errors made. Great, good. So you basically, what it would mean is that practicing is very effective. The more you practice, the less errors you make. If it was a super strong relationship, you would imagine it would be, almost vertical going down, meaning that only with a little bit of practice, you're able to reduce the amount of mistakes that you make in a performance down to 0. It's really important to consider these things. And I know it's very difficult the first time to do this. So I'm not expecting you have a complete mastery of all of this. but it's important to imagine what the situation would be like under different circumstances. And that's a really powerful scientific tool. So we could do this. And of course, because this is real data, I can actually run a statistical test on this. So I ran this in the R programming language in order to actually create these numbers. And from the statistical output, and don't worry that you have to know what all the numbers mean. Again, this is in the stats course. But the computer can actually figure out the line that we were talking about before. It can figure out exactly what is the best number to put on for this. So if you look where the red line shows, it actually shows the magnitude of the effect. It also gives us an intercept measure from the yellow arrow. And importantly to this, it gives us a p-value, which would mean a probability value, that compares whether or not the slope that we had was more extreme than what we would have expected in this circumstance if nothing actually were to have happened. So typically this threshold is set at 0.05, and if it's less than 0.05, it's considered statistically significant. And in this example here, we do have a statistically significant test. So again, I asked the class, do we have evidence of learning yet? Are you convinced that our experiment found evidence of learning? If so, why or why not? Matteo, wanted to unmute and answer this?
Yeah, the only thing I see here is that it stops around 13 minutes. And we don't know what happens next. And maybe it can change. Maybe it can be not less or 0.43 after 30 minutes. I mean, like you said before, the difference between 0 and 1 hour and between 4 and 5 hours is not the same.
Yep. Yeah, it's a great point that you bring up. So we can't extrapolate beyond what our data says. So we don't have anyone in our data set that practiced 200 minutes or someone that practiced 0 minutes. But specifically to the question here, is there evidence? Oh, great. I see from Maria's answer in the chat. If we can replicate these findings, yes, that is like the perfect answer in a lot of ways, right? But we'll look at that in a second. But it's a really important question to say, okay, what if we only had the resources to do this one experiment? So given just what we see here, is this enough? And did we also build evidence? So it's a lot to consider, right? We have so many things that we've thought about of this, and this is what some people hate and or love about science. But at this point, we would say, yeah, well, we have evidence to suggest that nothing is definitely not happening under the world of null hypothesis significance testing. I know it's sort of a weird way to take a break from, but I know how heavy this material can be. So let's take a 10-minute break at this point, and then we'll look at the second half of this, taking up with both what Maria and Marek has said. Can we replicate these findings? And is 20 people enough when we return? So on my clock right now, it's 5:17 in Berlin time. So let's return here and we'll start immediately at 5:27. So at 27, we'll be back and we'll continue your surprise giant lecture on statistics and learning. So I'm going to go away a bit in that time, but then I'll be back here at 27 past the hour. All right, if you can see my slides, just say I can see your slides in the chat so I know who's around. And we'll start off here with both Maria and Marek's questions. Thank you, Josephine and Marek. So Marek is saying, are 20 people enough? That's a great question. P-value is only talking about this in collection of events. And how can we make it representative? Another question in general. And then also, Maria's asking about replicating the findings, which we'll be talking about on the second half here, which is not really a half, it's quite small. So we've done this in our imaginary scenario. We are quite excited. So we got a significant p-value, meaning that the data says under the world of null hypothesis significance testing that we have definitely necessarily found something, but we know that nothing is not happening. So we have evidence to suggest learning is going on. So we have this statistical model that shows us something is happening, more importantly, in the direction that we predicted and very close to our predictions. So what do? We write up our little study, 1,000, 3,000 word article, and we send it to a journal because I want to tell all my academic friends about the experiment that I did with all of my German collaborators. So of course you have to wait a few weeks to hear back, and they write back and they say a couple of things. So I'll read this to you. So normally you get 2 people to review your thing, sometimes 3 or 4 if it's an intense journal, but this is a small little study, so we're not going to get 4 reviewers. So reviewer 1 says, the authors provide evidence of learning in effect, of a learning effect in practicing music after a week of playing. They found a significant effect of time practiced on number of errors. The regression model looks great, and I think this should get published. So they're quite keen on it. Reviewer 2, of course, is not as keen on this. They say, the authors provide some evidence for a learning effect, but they did it only with 20 people. So exactly what Marek said, over the course of a week. How do I know that this isn't just a fluke? Please run a second experiment so I'm more convinced about the results. We suggest revise and resubmit, meaning you have to sort of redo the manuscript and try again. The editor looks at what the reviewers say, and they say, well, after reviewing the reviewer comments, we would like to publish your study in our journal, but can only do this if you provide more evidence to satisfy our reviewer who remains skeptical of your findings given your sample size. So yes, smaller, if you have less people in there, you might not be as convinced. And importantly, what we're going to then run is a second experiment, just as Maria suggested. So if we see it twice in a row, hopefully that gives us more confidence in what we want to do. So if we do this experiment again, you'll find something actually does exist. We're hopefully going to get the same thing, but it's important to suggest and think about, do you think we'll get the exact same results? So answer in the chat, yes or no. Hopefully it's quite straightforward. So Marek's saying no. Gotten a no from Paula, probably not from Josephine. And importantly, what aspects of this experiment can you also modify to satisfy reviewer 2 to have more stable results? So we've talked about sample size. There are a couple other things that maybe we could think about, but it's important to ask yourself, what could you do to try to prove yourself wrong in this context? And it's important to consider, because if you can't prove yourself wrong, like that's good evidence to suggest that you have a good idea. So what do? We run it again with a bigger sample. So what do? I simulate some more data in R, and here's our new experiment. So this is a totally new set of data. We run the statistical analyses, and we get sort of the same results. So in the next slide, hopefully I have them next to each other. And if we look at these together, it's important to think, and maybe spend a bit of time on your own time this week thinking about this. Which of the numbers in our little statistical output, not knowing much about statistics at all, are similar? What numbers are different? How much are they different? And do you think that this evidence here will satisfy reviewer 2? So summarizing this for you, because I know it's a lot of information to look at, both times our p-value was below the 0.05 threshold. I don't know if you could see my mouse here, but I should be able to, oh no, that's not. See that this is 0.02 here from the slides, and then the corresponding second model that we ran from our second experiment, we have an even lower p-value. So a lower p-value doesn't necessarily suggest more evidence for it, but I won't get into that right now. But a lot of our numbers are kind of close. We have negative 0.39 here on the right for our estimate for minute practiced. And that's very kind of close to our negative 0.43, but they're not exactly the same numbers. So we run this, we write it up, and we send it again to the journal. Reviewer 1 says, great, Even more evidence for the effect. Totally accept. And reviewer 2 says, thank you for doing this. This makes me think that you indeed have found a robust effect of time practicing on errors produced in piano performance, accept. And the editor says accept. And then at that point, it gets typeset, put into a nice journal. And then you can tell all your friends that you have a new publication. But okay, so that's a big sort of like established narrative about how research might have happened, right? But we could have got lucky twice, right? And a lot of other things could have gone wrong in this process. In the last couple of minutes of class, I want to, 15 minutes, talk about some other things that may have happened that we should be aware of and we should consider. So before doing that, are there any questions at this point? So if you don't have any, say no in the chat. If you do, feel free to unmic or unmute. Okay, no questions. All very, very clear. I'm sure you're, taking it all in. I know it's a lot. Okay, great. Generally, no questions. So let's look at some things. What happens when the previous scenario doesn't happen exactly like this? So what would have happened if our results would have looked like this? So imagine we hadn't collected any data, and this is the first set of data that we did see. We look at our data. It appears that there's no relationship between number of minutes practiced and the number of mistakes in a performance. Being musicians yourselves, assuming you've all practiced at some point, how does that resonate with your experience as a musician? Is that right? What do you think? So imagine this was the data. What would you feel? Mateo's raised his hand. Take it away.
Maybe that's because we have to change our experimental approach.
Yep. So yeah, that's a possibility. We could have we might have designed a very bad experiment. So maybe this does not really capture learning that well as something. What else could have happened? All right, yeah, Noah says can't be true. Anyone else, especially from people I haven't heard from yet? 2 participants. Oh, I don't know. Let me see who they are. Paula?
There could be a lot of reasons, like, for example, if like a person had a really bad day and they usually, they practice a lot, but that day they just make a lot of mistakes.
Great, that's another possible example. Josephine?
Yeah, this is kind of going in the same direction. It's definitely possible that somebody practiced a hell of a lot and they still didn't manage to get it correctly, even though they might be good at their instrument or whatever. Possible.
Yeah, definitely. All of these things are possible. And you have to remember that when we're doing science, it's not like a, super, super reliable, systematic tool that gets the right result every time. And anybody that tells you that is probably never actually collected real data themselves, or they work in physics, because the world's a little more straightforward when you're not looking at human behavior within something like music learning. But it's important to think about these types of things, because like this data always reflects like real things that real people do. And just like the participants in our experiments, like we as experimenters can also make errors. So we may have designed a bad experiment, and it could have been that we just collected data and didn't find anything, even though learning actually does, or time spent practicing does actually reduce the amount of errors. Now, there are different ways to talk about the different ways that we could be wrong, and we have language for this, which I hope is my next slide. Yeah. So what might have happened if we saw the data that we just saw is that we failed to find an effect, even though one actually existed. Maybe we didn't have enough participants to detect this effect. That could be the chance. Or we just got a batch of data where it wasn't there. And of course, that could happen because we're dealing with things that are not deterministic, and chance is always an option, or something that could play into it. But statistics is there to try to help us sort of be more systematic about this. Or it could be that there is actually no effective learning, right? So maybe practicing literally does not help lower the amount of mistakes. And that is a reality that we should consider, even though it doesn't resonate at all with our experience as music psychologists. Now, living in this world a lot in terms of looking at data, thinking about the real state of the world, and trying to figure out stuff, we have specific names in statistics and the sciences for these different types of outcomes. And hopefully, I'd want you to get familiar with what these mean and also start using them when we start to have discussions about literature. So if you claim to have found something and it actually exists in the world, what you have found in that sort of state of the world is only referred to as a true positive. On the other hand, if you claim to have found something and it's not really true, so it shows it there in the data, but in reality, of course, we don't have access to because we don't have a direct line to God, but it isn't actually there, what we have done is we've made a type 1 error. Of course, having a type 1 error suggests the existence of a type 2 error, which we'll get to. Our third one on our list is if we claim to have not found something, and it actually doesn't exist, what we found is a true negative. So maybe I've looked at the effect of drinking ginger tea on the number of mistakes on piano, right? So I run this big experiment. I have people drink different amounts of ginger tea. I do the exact same thing that we did before, and I find no actual effect. And no effect actually exists, because why would ginger tea help reduce your amount of mistakes? This is referred to as a true negative. And then lastly, if we claim to have not found something, but it actually does exist, we've committed a type 2 error. So that would be if we would have saw the data that we just saw on the previous slide, we see and we claim that we've never found some sort of example of learning, but we know in reality, actually, if you do practice, the number of mistakes goes down. Again, this is more terminology that I want you to be familiar with. And we kind of think about this in relation to these different states of the world through both H0 or H0 and H1, or the alternative hypothesis. We'll return to the slide in a second, and it'll be here for your reference. But the best way to, I think, summarize this is something I saw on Twitter ages ago, which helps you never confuse type 1 and type 2 errors ever again. So if you remember that the boy who cried wolf, and I imagine that hopefully people are familiar with this story, caused both type 1 and type 2 errors in that order. If you don't know the story, please say so in the chat and I could explain it. But I think a lot of people have experienced this. But first, the boy who cried wolf, everybody believed that there was a wolf when in fact that there wasn't. This is a type 1 error. And next, they believed that there was no wolf when there actually was one. So if you substitute the word effect for the word wolf in this, you will have successfully understood type 1 and type 2 errors. Again, lots of new terminology, but we'll come back to it. So this leads to our last couple of slides that I want to get in the last 2 or 3 minutes here, in that what's been happening in psychology recently is something referred to as we're having something called a replication crisis. And this has to do with the idea of the findings not exactly being able to be sort of rediscovered time and time again. So there have been questions about if findings are reproducible in psychological sciences for maybe the past 15 years. Many of these findings that have been discovered have not been able to be replicated. So that would qualify as a type 1 error. So we have a lot of type 1 error in psychology. And in general, if you want to Google about this or read more about it, you can maybe do this for a final project. It's referred to as the replication crisis. And of course, there's a lot of different areas in science in which this is happening. So not just psychology and neuroscience, but medicine, artificial intelligence, food sciences, economics. And of course, music psychology is not to be forgotten from this list. But what it's done, and it's kind of the foundation for why I wanted to start the first 4 lectures of this class on music psychology about philosophy of science, is because it's caused a lot of people to think about what we do and what we want from our scientific questions and statistics. Not only is there a crisis of replicating, but there's also a crisis of generalizing. So in this specific example here, we might be able to replicate the effect of practicing on mistakes several times over, but maybe we couldn't do it with trumpet or flute players or who knows. But if we could do that in many contexts, it would be referred to as generalizing. So we want to know things such as, what if the effect in our previous scenario only worked with one specific type of music, or maybe it only worked with teenagers? So it's important for our theories to be able to also generalize and not just work in specific situations. So when people have tried to reproduce these types of studies, they tend to find a lot of less significant findings, smaller effect sizes, so things don't happen as dramatically as we think they do. And it's often very difficult to reproduce the exact experiment, in the sense that after time, people tend to lose stimuli, and people don't actually save their analysis scripts or data from like 10 or 20 years ago when they were actually doing this research. So if you're interested in this kind of stuff, there's this really great book I read recently called Science Fictions by a guy named Stuart Ritchie, who's also very active on Twitter. And he purports these different reasons as to why the replication crisis may occur. And some of these stories are actually quite grim and very depressing, I won't lie. But he attributes them to issues dealing with fraud, negligence, hype, and bias. We'll talk a bit about those next time. But we have some terms to review here for the slides, and sort of the larger takeaways from this whole lecture is that there are many ways for scientific research to not go well. We've saw in this lecture how much you really have to consider simultaneously when you're thinking about doing empirical research, and how important it is to be skeptical of the research that you do and you will eventually read about. Your job, and the point of this, is to try to prove yourself wrong. And if you can't, I think that's sort of good evidence that the theory and hypotheses that you want to investigate have something about them. So that's the end of our lecture for right now, but I want to spend 1 second and just direct your attention to something I'd like you to begin working on. So we don't really have tons of homework for this class, but if you look at our Moodle here, you'll notice I've added a link here. It says link here to collective glossary. And if I click this, hopefully it will actually just open up this tab here, or change this. And what I've done is I've taken all of the different terms and some of the people that we've discussed up until this point and made a big listing of them. So over the course of the next week, I invite you to, but you don't necessarily have to, kind of go into this document and start adding definitions to each of these terms in order to help your own review of things. You can edit this document directly. Everybody has edit access to it, so please don't go and just delete everything. I'm trusting you, just like in a scientific framework, I would trust you to handle our data correctly. But this is going to be sort of like a collective note-taking document for the entire class. The more you add to it, the more you're going to find it helpful. Of course, there's always the risk of one person doing all the work and no one else doing anything, but that's just kind of how life works. So if you want to work with this, you can. Eventually, I'll add terms here or there, but it's really more for your own review as you go through this, especially as we prepare for the final exam, which is really just going to be project-based learning, in which I'm going to ask you to critique and engage with a topic within the content areas that we'll start next week, using all of the terminology that we've talked about this week or the past couple of weeks. Are there any questions on that? I know I've given you a lot of material this lecture, but hopefully it's all helpful and of interest. If people don't have questions, you are more than welcome to leave, because I know I've gone a couple of minutes after the 45-minute mark. And I'll try to get the slides up in later next week for once we start getting to the other topics. So thank you for your attention. Yes, thank you, Alexander. I really appreciate it. If you have questions, I'll be here for the next 10, 15 minutes. And if you want to get cracking on the issues of glossary terms, you can sort of consider that a homework assignment. But really, it's for your own ability. Thank you, everyone. Much appreciated.